Happy birthday, Yogos.
Thank you, sir.
Thank you for inviting me. I'm happy to be part of this celebration of the wonderful achievements of Yogos, and of course, amazing achievements, I would say, not just wonderful. And I'm looking forward to also celebrating his birthday tomorrow. Let me say a few words about how I came about this title. So, I was monitoring the website, and I noticed, somehow the scope of the workshop seemed to be changing to much more technical. Because I started noticing a lot of the titles became data-driven. So I said, wait a minute, I was trying to review some papers on sparsity. And I realized maybe the committee has changed its mind, but just forgot to inform me. So I decided to be data-driven. So this title, that's why it has data-driven in it. Because I felt that the website had everything had data-driven in it. And I said, how can I not be data-driven if I'm going to be in a workshop that is data? That's the plan. So let me start with the problem. I think most of you already are familiar with this, but it's good to get notation in place. We're looking at an underdetermined system equation. Y are your measurements. P is often referred to as the dictionary or the sensing matrix, and X is the parameter of interest. And since this is an underdetermined system equation, there are many solutions. So you need to put some constraints in order to be able to identify the solution of interest. And in this context, the X is known to be sparse. That means many of the entries are 0, except for a few non-zero entries. The location is not. When I first came about this problem, though, this was in early 90s. In those days, in the signal processing society, linear algebra was a big thing. SVD was in, eigendecompositions were in, everybody knew least squares. So when I saw a linear system equations, I was very nervous that there's nothing research worthy. When you have a system of equations, particularly having a linear system. So I was very nervous when my student came to me with this problem, because she was looking at a problem on MEG. So I said, the linear system equation, please go to the math professors, make sure this is still something you can work on. Okay? So I will share some early work, because she had come up with a reweighted L2 algorithm for solving the MEG linear inverse problem. So as a good advisor, I was trying to make sure she was not solving something that was in textbooks. So we did some research, and it was very difficult actually to find papers on sparsity. Of course, it was technology, partly the limitation of technology. You didn't have Google Scholar where you could go in and just simply type, okay? But also it was hidden in application area. So we really had to work to identify that people were working on sparsity. For instance, I was able to identify the paper by Singer and al. Only because I was doing some speech coding work also. So when I read their paper, I said, oh, they're doing sparsity. But I started looking at this and I realized that lots of people are doing the sparsity was known, but maybe in a very limited context, generality was not discovered. People were doing it, and most people were applied, so they solve the problem and move on. Okay. So I didn't think it would be of general interest. And as I worked on this problem, I began to see sparsity elements. As the saying goes, if you have a hammer, everything looks like a nail. So I was also trying to convince myself that this problem does have merit. So I'll give you an example. I teach a course in DSP. I teach the FFT, and typically, most of you who taught a DSP class, you try to find out the resolution of FFT. You put two complex exponentials, and you give data to your students, and you say, can you resolve these exponentials? And you move them closer, and of course, at some point, they're there. Till I started working on this, I never really saw the connection to sparsity. Let me try and explain. Because if you give me 64 samples, we know an FFT is just fitting complex exponentials. People were taking a 1024 FFT. What I said is an overdetermined system equation. You are fitting 1024 exponentials to 64 samples. This is really the problem. And what solution did you find? So the first time I actually asked it, that question from a linear algebraic point of view, I knew it through convolution. It's a window, of course you're convolving, and you're getting this blurring because of the window. Okay? But I never really thought, that's the thing, sparsity is right there. I've been teaching it for the last 10 years, but never really saw it. And of course, compression is all about sparsity. So I realized it's probably real. And then I started looking around for people who were working on sparsity, and of course, your arm was working on it. So I teamed up with him to actually organize a special session at ICAST in 1998 to try to see if I can generate more interest in sparsity. This was 1998 ICAST in Fiat. And you can see there was Donahoe had a paper in that section. I come to invite people from different disciplines to see if I can get them to vision. And I think you're on helping me with this. I'm not sure I was successful, but I was successful in convincing myself that this problem is still interesting. Let alone not the community, but I still thought this is still, and Yoram is working on it, must be. So I always follow leaders. Of course, the papers in 2006 was the watershed moment. Things just took off. Right? So, looking back now, I think sparsity is a tool in many, in almost most signal processing tools. Everybody's heard about it, and people are applying it in many. So I thought I would do a brief review. Originally, I was trying to do a more review, but then when I saw the data-driven approaches, I changed my stance. So I decided to do a Google search, and of course, there are too many papers to list. Okay? And so we need a day session just to review all the work that Yorgos has done on Sparse. Here's a snippet. I took 6 papers out of the infinity that are there. I'll say a few words about the first 2. I'll go on to the data. The first one is on communications, where he's looking at a multi-user system, multi-user CDMA system. So the number of users are large, the number of active users is small. You don't know who's on at any given time. Really the work sparsity applies. I think the formulation that he uses is very interesting. They decided to add a new symbol to the constellation, which is 0. And the prior on that constellation symbol is different from the non-zero. And that leads to a nice base map estimate, where you're actually regularizing using the 0 norm on the user. So they're trying to generalize it. Very interesting formulation of applying sparsity to multi-user. The second one, of course, is sparse linear regression using distributed agents. And I think I noticed distributed agents is a very popular topic. He loves distributed agents and distributed optimization. So we're looking at the same Lasso problem, but then how do we distribute this Lasso problem to agents that are not allowed to share data? So you can split the Lasso problem into separable problems. And then using ADMM techniques, we have a very clever algorithm that is able to solve the Lasso problem in a distributed. And I noticed in the paper he has a lot of interesting applications. And one of them is a targeted radio. If you look at these papers, by the way, you will realize that the scope of the applications. You don't need anything. Just looking at Yorgos' paper, you can tell sparsity has many applications. You cannot convict. He has touched upon so many applications in space. So when I was So there's work on spectrum cartography, cognitive radios, okay, connection to robust statistics, power line voltages, this goes on. I'm still compiling those. It turns out Yorgos has not touched on all that. There are a few still there. But I think just to highlight that there are, the list keeps growing, and it's really up to the imagination about now that this tool is available, it's up to the tool of the application. So let's look at the algorithmic trend of the approach. I will try, this is my own way of classifying, but I have not listed all the classifications. This problem is known to be NP-hard in general, and so you do need some practical and meaningful. So there are these search techniques that mapping pursuit, orthogonal mapping pursuit, and there are many variants on that. Then there are these techniques that minimize sparsity, surrogates of sparsity. So we want to minimize this L0 pseudonorm, which we don't know how to do. So we'll come up with these surrogate measures and regularization methods. The L1 is very close because of the theoretical guarantees that are associated with it, is very popular. But then there are many, like the reweighted L1 and the reweighted L2. Just as a suggestion, if you're going to do L1, I suggest doing reweighted L1. This is for practice. That's the reason look, okay, and you can't do any worse than the L1. Then, of course, the Bayesian methods, they tend to try and guide the solution, just like in the previous case, we were guiding the solution through this regularization penalty, so you try to do it properly. And then there are a whole bunch of them. My favorite, of course, is Sparse Bayesian learning, and I'm going to talk about that when I go towards data driven. So now, with machine learning and deep neural networks, there's a whole bunch of papers now, a lot of work that is appearing now in applying these to the sparse algorithm. So I want to say a few words, and I'm joining the bandwagon, so I want to say a few words. The potential benefits. Whenever we do model-based techniques, the nice thing about model-based techniques is once you solve the problem, it's done. But there are some hyperparameters, there are parameters that you use, like in a regularization case, how do you tune this problem? Well, you can unfold these networks, and there's a lot of work on unfolding algorithms, tuning the parameters, tuning things that you're not for sure. I think the second one is probably more pertinent to this problem. If you cannot find a solution, the problem is, the optimization problem is very intractable, and maybe deep networks can solve it. We were talking to Ram the other day, just a few minutes ago, and he's saying all values and things, all optimization problems can be solved. You just have to throw it in and don't worry about local minima, global minima, just that. Of course, dealing with nonlinearity. This is for real. These are problems that we deal with, we sanitize them. So most systems have nonlinearities, and we need to do it. And one bit compressed sensing is an example. These here, one bit passing mark. So certainly to deal with nonlinearities, we end up with it. And of course, there are problems that are hard to model. I should you're on the next talk today in the morning showing us how we may not be able to model them, but we can use the machine learning approach to do that. So let me talk about how maybe we are trying to deal with this in this process. One way of doing it. This is the best I know. This is what I know well, which is why I'm sticking to it. I don't want to say something that I don't quite know. So I will look at the sparse Bayesian in this framework. I want to cover the method. I want to motivate the deep learning strategy. So this is a problem where you put a prior on X, assume all the X's are IID, Gaussian, mean zero, unknown value. It's a much more generalized version of this, but this is simplest one I know. This is falls under empirical way. So you're trying to learn the parameters of this prior. So you try to find the variances, and by finding the variances, you try to find Sparse. So you pose a maximum likelihood problem, where you say y given gamma, what is the maximum likelihood estimate of gamma? Of course, everything is Gaussian here, because x is Gaussian, z is Gaussian, so it's very tractable. So you can actually write the underlying optimization. And you will get a problem where you're minimizing the log determinant, which comes from the covariance of y, and then, of course, the exponential. Just as in terms of people who are familiar with compressed sensing, but maybe not in this study, the log determinant is concave in the parameter, and so promotes Sparse. The second term, which is the sigma y inverse yy, is actually a model fitting. It also has this model fitting plus regularization form. This problem, because of the concave part, there is no guarantee of guaranteed local ray minima, and so you have all these issues. It's not a simple optimization problem. So you can come up with many recipes. So can be an Sparse. So here's a sampling recipe just from the original tipping kit. So here has a multiplicative update. By the way, I have changed the formulas to make them look convenient for you. So in some sense, you won't find the formulas in the paper, but they'll be rewritten, but you can get it very easy. One is a multiplicative update, where you take your old estimate of gamma and you multiply, as the name suggests, by a factor, T1 by T2. And you are. T1 depends on y and on the old estimate of the gamma. T2 is purely a model driven term. So it can be computed based on the old estimate. You want to keep in mind, think about T1 and T2. You can run the EM algorithm, and it turns out if you rewrite the EM, it also is doing T. You can generalize the multiplicator, okay? And you say, I can raise it to the power P. And we can prove actually that it reduces the objective function in this way. I don't know what happens after that. You can experiment, okay? But I offer no guarantees. As soon as you see this, you can say, if you saw the last one, if you were a model-driven person, you can optimize on P. Maybe I will do some kind of trick and I'll try to figure out, is there an optimum P? And this is really the challenge. Once you have an optimization problem, and there is no simple way of optimizing it, no guarantees, we apply majorization minimization, and we try to find a way of getting to a solution. But there are so many ways in which you can majorize this function. Every time you do this, you get a new one. Okay? So which one do you choose? Okay? So I say, let the DNN decide. Okay? So you can learn, you can use machine learning to see if you can do something which capitalizes on this lack of clarity. And hopefully, it will provide you clarity eventually. Not yet. So here's an example. We run EM and in tipping. The left side, this is applied to an array processing problem. The left side is talking about the probability of support the problem, how many sources can be identified successfully. And the right side is the mean score. So it looks like the tipping algorithm actually is better than the EM in support. But you run a different set of sensing matrix, and it changes. So you can't say I'm going to use tipping of procedure because that is the better one than the EM based on just the simple example. I will show you one in a few minutes. So we decided we're going to do a machine learning strategy. And the motivation for this is based on this formula. The way you can think about this, if you want to abstract it, there's a T1, there's a T2, and an old gamma. And you're trying to find a mapping of these three parameters to the new gamma. What should that function be? So let me search for this function and see if I can find a better mapping by using this. This is, so of course, now you have to come up with a fixed number of iterations so that we can come up with this deep learning structure. We have to choose a number of iterations. And these iterations are fed in T1, T2, and Y. So T1, T2 are computed just like, I'm not going full blast data. I'm just simply figuring out how to map the old gamma to the new gamma and looking among its more broader class of mapping. And then we come up with this. The reason I argue for this structure is simply not only do we find this mapping, if you change the dictionary, all I have to do is change T1, the computation of T1, T2. I don't need to change the network. I don't need to retrain the whole network because I changed my sensing. Each layer has 5. Finally, this is an R. At this point, this is why I also love machine learning. If you have time on your hand, you can play around with structures. One day, voila, you found the right plot. And then it works like a charm. Now you know you have a winner. You have to figure out how to do it. So this is a 5-layer network that we use, and we love stick connection. It's true in all deep learning. Stick connections are very valuable. By the way, this is just a second-year graduate student. He just started recently, and he could produce all these results better than all the EM chipping results we were doing for the last 10 years. It didn't take him long to produce better results. So you can see the first top one, the blue curve, is the EM applied to in this case, an array processing. What we find is, of course, it improves the ability to find support and outperforms the classical technique. If you look at this problem, though, you'll find that chipping is doing better than EM. If I change the sensing matrix to a random matrix, EM is better. So if I was choosing between EM and chipping, I'm really in trouble. I have to go case by case. But the EM structure is still simple. So there is reason to do, I think in my case, sometimes in some of these problems, I'm doing it gingerly. In my mind, I am still not 100% doing input all the way to output. But I think there's interesting opportunities. So here's my summary. I think clearly sparsity is continuing to grow. People like Google's, it's unbounded. I think there will be more and more applications. I think DNN-based data-driven approach is also interesting opportunities. And I think we will find certainly improved performances. When the problem become more challenging, where we don't have really model-based methods, we will still be viable solutions. Thank you. Any questions there?
Just out of curiosity, did you transfer the parameters? Did you transfer?
Yeah, sorry.
No, go ahead.
Did you transfer the parameters from the first sensing matrix to the second one, or you did it?
No. We did both. It turns out, this is one of the questions we're going to answer. What would be a good matrix to train on so that when you transfer, you don't lose that performance? At this point, random matrix seems to be a good way to train. Okay. But I don't, the answer is, as I said, it's still important. All right, good.
Since T1 and T2 are also dependent on gamma, right? So could you also try to learn them and just have gamma as some kind of input that happens?
Yeah, the gamma is, okay. Maybe let me make sure I understand your question. The gamma that goes into the T1, T2 block is the output of the DNA.
Yeah, so but suppose you put A and Y always in.
Oh, yeah, absolutely.
And then you try to learn also the T1 and the T2 because that's also kind of...
Right. The reason we didn't do that at this point, let's say, yeah, yes, because the A matrix seems to be much larger, and as a result, the network becomes very large, complexity is very high. So the answer to your question is, yeah, sure, we could learn the functional form of T1. It's like as I said, we are trying to keep as much as possible and still show improvement.
Thank you, Bhaskar.